Good morning, my students. We are going to study the magnetic force on a current carrying wires. This is the topic. Magnetic force on a current carrying wires. If you have a magnet and this is the straight wire carrying electric current due to the presence of battery, which is DC source, not alternating current, but it is direct current. Current passing through the wire enclosed path between two poles of magnet. The magnetic field come out from north to south, When we move this wire in a vertical position, the wire making cutting for the magnetic flux, so it will be produce a force to move this wire. Like device like a meter, voltmeter, motor, this is the idea for many devices like a meter, voltmeter, moving coil galvanometer, voltmeter, ohm meter, and electric motor or DC motor. Operate using magnetic force effect. Magnetic force effect. The force on a wire carrying electric current or in a conductor, when the wire carrying current through wire, which is called conductor, the wire is called conductor, is placed in magnetic field, permanent magnet or fixed magnetic field. Force is produced on the conductor. Force is produced in the conductor due to the difference in magnetic flux densities between two sides, which it moves from more denser side to less denser side. The direction of the force always perpendicular. To make cutting or change in the magnetic flux or variation in the magnetic field linked with the conductor to both current and magnetic field. If the current or magnetic field direction is reversed, the direction of the force will be reversed. If the direction of the current only is reversed, the direction of the force will be reversed. If the direction of the magnetic field is reversed only, the direction of the force is reversed. If both of them, current and magnetic field, are reversed, the direction of the force does not change. If the current and field are reversed, the direction of the force remains unchanged. If the current flows in wire parallel to the field, no force, because when it moves parallel, there is no change in magnetic field. If the wire moves parallel, it will not change in magnetic field. This means that there is no change in magnetic flux and there is no force. The force acting on the conductor increases by all the factors affecting on the force. Factor affecting on the magnetic force acting on a conductor increases by increasing current. This force F equal B I L sine theta. This means that F equal Bell sine theta. B, it is the magnetic flux density resulting from the magnet from north to south. I is the current intensity passing through the conductor. This is the current intensity passing through the conductor from this source in the battery, VB battery, or DC source of electric current. L is the length of the wire. This is the length of the wire L. Sin theta, the angle between the magnetic field and the wire. The angle between this is the wire and this is the magnetic field. The angle between them is called theta. First, by increasing the current in the conductor or increasing the length of the wire placed in the magnetic field or increasing the magnetic field strength or intensity of the field. Force on a current coil like this is called coil or armature converted from two sides. This coil carrying electric current affected by two equal and opposite forces, which produce magnetic torque. Due to this force equal BIL sin theta. This force equal BIL sin theta. This force equal the first but in opposite in direction, and there is a difference between them. This is the distance between the two forces is called the vertical distance. So magnetic torque is produced when a coil carrying electric current between two poles of magnet affected by magnetic torque tau equal pi sin theta, due to the presence of two equal forces in magnitude but opposite in direction, because B is the magnetic field resulting from or magnetic flux density from two poles of magnet. Current intensity is the same current intensity. Length, this side equal and parallel to each other and perpendicular on it. So they have the same equal forces but opposite in direction. When a current carrying coil is placed in magnetic field, it starts rotation the current in the coil of the two sides. These sides carrying a current, but these sides, when during motion parallel to the magnetic field, theta equal 0, sin 0 equal 0, this means that the magnetic torque equal 0. The current in the two sides coil opposite direction. So the force in the two sides acting in the opposite direction, perpendicular to the current direction. And this produces turning effect, which is called torque. Torque is called turning effect. Turning effect is called torque. If the current or the field direction are reversed, the coil spin in opposite direction, force reverse it in direction. If the current and field direction are reversed, the coil spin in the same direction, the same force direction is the same. Coil turns or spin faster by increasing current intensity, by increasing number of turns of the coil, because torque equal pi sin theta. This means that when the number of turns of the coil increases, it moves quickly. Increasing a magnetic field when we use a stronger magnet, but this is called DC motor. DC motor coil connected with the commutator. This part is called the commutator, and this is called the brushes F1 and precious F2 made of graphite. And this is the source of electricity, so the coil carrying electric current between two poles of magnet produces turning effect or magnetic effect. Turning effect or magnetic effect. The principle of electromagnetic induction. If you have a straight wire between two poles of magnet, and this is the galvanometer used to determine the direction of electric current, when we move this wire up and down, this is the direction of motion, up and down between two poles of magnet, we make cutting to the magnetic flux lines. So current is called, but it is termed induced current. Is termed induced current. Generators operation using the principle of electromagnetic induction. This process or this phenomenon is called electromagnetic induction as described below. When moving wire in a stationary magnetic field, a constant magnetic field between two poles of permanent magnet. When moving wire perpendicular to cut the magnetic flux, but when it is moved parallel, there is no induced current. Across the magnetic field, induced EMF and therefore induced current are induced in the wire, while EMF or current produced from the battery is called current and EMF. While EMF produced by this method is called induced EMF and the current is called induced current. This is because the magnetic field is being cut by the wire, linked by the wire. A small current is detected because moving coil galvanometer used to measure very weak current intensity, not by high current intensity. High current intensity measured by using ammeter, but this is called sensitive ammeter, milliammeter, microammeter, or moving coil galvanometer. A small induced EMF could be detected using millivoltmeter to measure the potential difference. Another type, voltmeter, to measure electromotive force EMF, millivoltmeter. Or microvoltmeter can be used to measure very small value to measure it. The motion of the wire against the magnetic field moves downwards. The wire moves downwards. The magnetic field cuts. EMF and the current are induced in the wire. And the pointer deflects in one direction, the pointer of the galvanometer in this direction. And when we move up, it moves in the opposite direction. This means that moving coil galvanometer can be used to determine the direction of the current and mean that the current is alternating current, move up and down, alternating current, opposite to the second current which is produced from the battery, which is a direct current. Current move in one direction, not in the two opposite direction. In this process, current moves in one direction only in case of direct current. But by using galvanometer, this is alternating current, moves into two opposite directions. When the wire moves upward in the motion, the direction of motion is reversed. The wire moves up. The magnetic field cuts, but in the opposite direction. Induced EMF and induced current in the opposite direction is produced, and the pointer deflects in the opposite direction as well. If this process is repeated up and down, magnetic field is cut back and forth. The pointer deflects back and forward to form alternating current. When it is parallel or stationary, when the wire moves parallel, the wire moves, this is the direction of motion of the wire, and this is the direction of the field. This wire moves parallel to it, it does not cut it. So there is no variation in the magnetic field. We observe that the pointer at 0 does not move. Moving coil galvanometer does not change. There is no induced current. There is no induced EMF when the wire is parallel to the magnetic field, or when the wire is stationary between the two poles of magnet. The magnetic field is not cut by the wire, so there is no induced EMF. The pointer stays still, halfway at 0. Induced EMF and induced current increases by moving wire at a high speed, because V equal delta X divided delta T. When the speed of cutting increases, the time decreases. While EMF equal minus N delta phi M divided delta T. During short time, induced EMF increases because it is inversely proportional with the time, inversely proportional with the time, while the velocity inversely proportional with the time. At high speed, the process takes place in very short time. When the time is very short, induced EMF increases. This means that moving the wire at higher speed produces high induced EMF. Or increasing the magnetic field strength by using a stronger magnet, or moving more magnets close to each other by using more than magnet close to each other, or wrapping the wire into the coil, wrapping the wire into the coil by using big numbers of wires, In this case, the magnetic field increases and the induced EMF increases. The motion of magnet inside the coil. This is the magnet. If the magnet is blown into the coil, this is the direction of the field. The magnetic field transfer from north to south. During this coil is called solenoid. When it moves, blown it into, or blown it into the solenoid, the pointer deflects in a certain direction. This means that induced current are produced. Induced is produced. Moving magnet near the coil or solenoid. This is called solenoid or coil. While the moving power magnet toward the coil, EMF and current induced in the coil. This is because the magnetic field cuts by coil as the magnetic moves and out, move into or out. In the second process, it moves away from the magnet, and the deflection, cutting takes place, but in opposite direction. When we go towards the solenoid, the magnetic field increases. This is called the change in magnetic flux, or rate of change of magnetic flux. When we move away, the magnetic flux or rate of change decreases. Due to this change, induced EMF is formed and induced current, but in opposite direction. Motion of magnet into the coil. Magnet moves in. Magnetic field is cut by coil. EMF and current are induced in the coil, and the pointer deflects in one direction, out of the coil or pulled out. Motion is reversed. The magnet moves out. Magnetic field is cut, but the coil is opposite direction. EMF and current induce opposite direction, and the pointer deflects in the opposite direction. in the opposite direction. When the magnet is stationary near or inside the coil, magnetic field does not cut. No induced EMF and no induced current, and pointer stay at the middle. At the middle does not move. Pointer stops at 0 and does not move. Example. Describe the movement of the pointer in each of the two cases. If the magnet is pushed into the solenoid and then brought to rest with its north just inside the solenoid, the magnet is then pulled out to the left of the solenoid at high speed. In the first state, the pointer deflects and then returns to 0 because it becomes at rest. While in case of the movement in the opposite direction, pulled out, but with high speed, the pointer deflects more, but in opposite direction, then returns to 0 after stopping it. This means that induced EMF increases by moving magnet at high speed. Using a stronger magnet, increasing the number of turns of the coil. Increasing the number of turns of the coil means that a change in the magnetic field. A change in the magnetic field. Goodbye and good luck.